Have you ever dreamed of traveling across the universe in the blink of an eye, skipping past galaxies and arriving at a distant star system faster than you can say warp speed? Science fiction is full of incredible ideas like this, often using a concept called a worm. But what if I told you that these cosmic shortcuts aren't just fantasy? What if they're actually rooted in the groundbreaking work of one of history's greatest minds, Albert Einstein? Today, we're diving deep into the mind-bending question: can wormholes really exist? Let's start with the basics. Imagine the universe as a giant, flat sheet of paper. To get from point A to point B, you'd have to travel across the surface. That could take millions of years, even at the speed of light. Now, what if you could fold that sheet of paper, bringing point A and point B right next to each other? Then, you could just punch a hole through the paper to create a tunnel, a direct shortcut. That, in a nutshell, is a worm. Officially, it's called an Einstein-Rosen bridge, and it's a hypothetical structure connecting to different points in space. This wild idea comes directly from Einstein's theory of general relativity, published in 1915. This theory completely changed how we understand gravity. Einstein showed that gravity isn't a force pulling objects together, but rather a curvature or warping of space-time caused by mass and energy. Think of placing a heavy bowling ball on a trampoline. It creates a dip, and any smaller marbles rolled in nearby will curve towards it. That's gravity. Planets orbit the sun because the sun's immense mass creates a huge dip in spacetime. So, where do wormholes come in? Well, in 1935, Einstein and his colleague Nathan Rosen were exploring the mathematics of general relativity. They were studying the extreme gravity of black holes and found a peculiar solution to their equations. Their math suggested that a black hole, a point of infinite density, could be connected to another point in space. This connection, this bridge, was the very first theoretical model of a wormhole. It was a purely mathematical discovery, a ghost in the machine of relativity. They envisioned it as a tunnel with two ends, or mouths, located at different points in space and even time. This is where things get truly exciting. If wormholes exist, they could be the ultimate cosmic express lanes. A journey to the Andromeda Galaxy, our closest galactic neighbor, would normally take over 2.5 million years traveling at the speed of light. With a stable wormhole, that journey could theoretically be shortened to just a few minutes or hours. You could step through one end in the Milky Way and step out the other in Andromeda. It's the kind of technology that would completely revolutionize humanity's place in the cosmos, and it doesn't stop with space travel. Since wormholes connect 2 points in spacetime, they could also potentially be time machines. Imagine one mouth of a wormhole is kept stationary, while the other is taken on a journey at near the speed of light and then brought back. Due to time dilation, a phenomenon also predicted by Einstein, time would pass more slowly for the moving mouth. When it returns, it would be in the past relative to the stationary mouth. Step through the stationary end, and you could emerge from the moving end at an earlier point in time. Mind-blowing, right? But before you start packing your bags for a trip to the Jurassic period, we need to talk about the massive, and I mean massive, problems with wormholes. The original Einstein-Rosen bridge had a fatal flaw. It was incredibly unstable. The moment anything, even a single photon of light, tried to pass through it, the tunnel would collapse violently into a singularity, crushing whatever was inside. It would open and close so quickly that nothing could ever make it through. So, Einstein's original wormhole was more of a theoretical curiosity than a practical method of travel. So, is that the end of the story? Not quite. Physicists are a stubborn bunch, and they didn't give up on the idea. The key to keeping a wormhole open is to find something that can prop it up against the crushing force of gravity. This is where we enter the realm of truly exotic physics. To stabilize a wormhole, you would need something with negative energy density. We call this exotic matter. Now, what on earth is exotic matter? It's not just something we haven't discovered yet, like a new element on the periodic table. It's matter with properties that defy our everyday understanding of physics. Normal matter, like the chair you're sitting on or the air you're breathing, has positive mass and exerts a positive, attractive gravitational force. Exotic matter would have to do the opposite. It would need to have negative mass or generate a kind of anti-gravity, pushing space-time apart instead of pulling it together. This repulsive gravity is what would be needed to counteract the wormhole's natural tendency to collapse. Does exotic matter exist? Well, we've never observed it directly in a lab. It sounds like pure science fiction. However, there are hints of it in the bizarre world of quantum mechanics. A phenomenon known as the Casimir effect shows that even empty space, the vacuum, is fizzing with energy. In certain configurations, it is possible to create regions where the energy density is technically negative compared to the surrounding vacuum. The effect is incredibly tiny, far too small to stabilize a human-sized wormhole, but it proves that negative energy isn't completely impossible according to the laws of physics. So, let's assume for a moment we could somehow get our hands on enough of this exotic matter. We could then, in theory, build a traversable wormhole. But how would we even find or create one in the first place? Some theories suggest that microscopic wormholes might have popped into existence in the fiery chaos of the Big Bang. These quantum-scale tunnels could still be littered throughout the universe. Perhaps an incredibly advanced civilization could find one of these tiny wormholes and use exotic matter to inflate it to a usable size. Creating one from scratch would be an even greater challenge, requiring technology far beyond anything we can currently imagine. You'd need to manipulate the fabric of space-time itself, generating immense amounts of energy to bend it and create the tunnel. The energies involved would likely be comparable to the output of an entire star. Even if we managed all that, there are other dangers. The journey through the wormhole itself would be perilous. You'd likely experience extreme tidal forces that could rip you apart. There's also the risk of intense radiation. The connection between two distant points could allow high-energy particles to feed back and amplify within the tunnel, essentially roasting anyone who tries to pass through. And then there are the paradoxes. If wormholes can be used for time travel, what about the classic grandfather paradox? What if you go back in time and prevent your own grandparents from meeting? Would you just blink out of existence? Some physicists, like Stephen Hawking, proposed a chronology protection conjecture, suggesting that the laws of physics themselves might conspire to prevent time travel and its associated paradoxes. Perhaps any attempt to create a time machine would inevitably fail, with a wormhole self-destructing in a blast of radiation. So, to sum it all up, can wormholes exist? According to Einstein's general relativity, the answer is a tentative yes. The mathematical framework for them is there. However, making them traversable requires a substance-exotic method that we're not sure even exists in the quantities needed. And even if it does, the engineering and safety challenges would be monumental. For now, wormholes remain on the fascinating boundary between established science and theoretical speculation. They push our understanding of the universe to its absolute limits. While you probably won't be booking a weekend trip to another galaxy anytime soon, the very possibility that these cosmic shortcuts could be real is a powerful reminder of how much we still have to learn. Einstein's theory opened the door, and now it asks up to future generations of scientists to see if we can ever walk through it. Thanks so much for joining me on this journey through spacetime. If you enjoyed this deep dive into theoretical physics, make sure to hit that like button and subscribe for more videos exploring the biggest questions in science. Let me know in the comments, what do you think, are wormholes real? We'll see you in the next one.